All right. So, a very good evening, everyone. So, today we are into the 10th lecture of social media analytics, and we are going to start with the link predictions. Okay, so I hope I am audible to everyone and my screen is visible. All right. So, up till now, we have covered some very important topics in social media analytics. So, some of these were identifying important nodes in the networks. So, for that, we have seen various algorithms to find the influential or the most important nodes in the networks. Okay, so moving from identifying important nodes in the networks, we moved on to the next set of problems that was identifying communities. So communities are subset of nodes that are more connected within themselves than the rest of the networks. So we have seen a lot of algorithms to identify the communities. Okay, so now after completing the identification of important nodes and identification of communities, we are going to move to the next important set of problems, that is link prediction. Okay, so in today's class, we are first going to understand what is this problem of understanding, link prediction. So we will be understanding this problem. So basically it is of two types. So I will be explaining you in detail that what all are these two types, how these two types are different. Then we will try to motivate ourselves with the applications. Okay, so we will be discussing various applications of link prediction. Then after that, we will be seeing that link prediction is a binary classification problem. Okay, so basically this link prediction problem is a binary classification problem. So if we have a classification problem, then how can we evaluate it? Okay, you can form an algorithm for predicting a link in the network, but then how you will evaluate its effectiveness, how you will evaluate that whether the algorithm that you have designed is correct or not. For that we will be seeing various evaluation matrices. After that, we will be moving on to the algorithms. We will be seeing different link prediction methods. So in today's class, we will be mostly touching upon local similarity based link predictions and global similarity based link predictions. So this is the summary of the topics that we are going to cover in today's lecture. Okay, so first of all, what is link prediction? Okay, so basically you have this algorithm, you have this network, and in the network you want to identify that whether these or and this network are connected or not. Okay, so this is the problem of predicting the existence of link between two entities in the network. So we will be predicting that whether two entities in the network are connected or not. It involves several research communities ranging from statistics, then network science to machine learning and data mining. Okay, so in link predictions, we have various algorithms from machine learning. We have various matrices that are used to, check whether the particular algorithm is correct or not. So in those cases, we use statistical measures and then we also use data mining techniques to help. So this is an active research area and you will find a lot of papers on link prediction. So there are a lot of algorithms that are formed to identify links between the nodes. It helps in predicting the state of dynamic network at future timestamps. Okay, so first of all, we will try to understand what is dynamic network. Dynamic network is a network that changes over time. As the name suggests, dynamic network is a network that changes over time. For example, a social network, the real word social network. Today we are friends with someone and tomorrow we might be friends with other people. Then like after few days we stop talking to a certain person. Okay, so there are the links that are generated over period of time, and there are links that are deleted over the period of time. So whenever the networks are changing over the time, we call such network as dynamic network. So we can predict that whether in future there will be a connection between two nodes or not. So this is one of the one part of link prediction. Okay, so basically this link prediction algorithm, the link prediction problem, it can be divided into two types. Okay, so there are two types of link prediction problems. The first one is in the static networks. So you have a static network, and in the static network, you want to see that whether there's a particular link that is missing. Okay, you want to check that like whether this particular network is complete or not, or whether we have missed a particular connection or not. So in order to predict the missing links, we can use link prediction algorithm. So this is one part of seeing this problem. This is one way in which this problem can be seen. Other is in dynamic networks. So in dynamic networks, okay, you want to see that at t timestamp, there were certain connections. Now at t dash timestamp, whether there will be certain addition of connections or not. Okay, so these are the two types of link prediction problems. Now, moving on to the applications of link prediction. So, link prediction is a very important problem in social media analytics, and it has a lot of applications. So, starting from online social network analytics. So, in online social networks, for example, in Facebook or in Instagram, you might have seen that you get recommendation of friends. So how do you get these recommendations? So maybe the people who these platforms suggest you to be friends. So these recommendations may have a lot of common connections. So you have certain friends, and your friends have common connections with these particular people that are suggested to you on these online platforms. Okay, so so these recommendation, the friend recommendation is through link prediction. There are algorithms that these platform implement in order to recommend you the friends. These are called link prediction algorithms. Next, so like in Instagram, you might have seen that you talk about certain thing and those kind of reels are suggested. Okay, so these type of suggestions are also by link prediction. So maybe like this is just like I am assuming that maybe our phone is listening, and the phone takes an input, whatever we are speaking, it takes an input, then it predicts link. It predicts links to the reels, and this is how we get these reels suggested. Okay, so there can be different, we don't know about the actual algorithms, but we know that this is an application of link prediction. Then coming to the e-commerce websites. Okay, in e-commerce websites, like for example, in Amazon, so you go to buy a product, for example, like I am buying a bottle, a water bottle. Okay, so when I buy a water bottle, I get another link. Okay, another link saying that like this product was bought along with this product. Okay, so like many a times we see these kind of suggestions and recommendations. So we see that with the bottle, maybe there will be tiffins that are suggested. Okay, and you will definitely see that with a water bottle, you will never get a suggestion like a fan. Okay, so why this is so? So this is so because these particular platforms, they have these links predicted between the items. Okay, so this is another application of link prediction. Now coming to police and military application. So you might have seen this documentary on Osama bin Laden. Okay, so in that documentary, it says that how Osama bin Laden used to communicate with his trusted person. So they have created this Google page. They have created a Google ID, and on the Gmail ID they opened the draft, and on the draft they used to write whatever like they want to communicate. So once the other person read that message, they will delete that message from the drafts. Okay, so they avoided sending the messages over the network. So this is how they used to communicate. And also when the US military, they caught Osama bin Laden, it was due to a phone call. Okay, so with this phone call, they predicted certain links, and due to those links, they got to know that the location of Osama bin Laden. Okay, so you can see that the link prediction is very, very important, and it has a lot of real world applications. Now, we have another application in a network reconstruction. So you might have, like, if you are analyzing large networks using, for example, Twitter data. Okay, so generally what we do network scraping. Okay, so in the scrapping, you do not get the entire data. So there will be certain missing links in that data. So now you want to complete those links. So for that completion of the network, for the completion of the data you have taken, you can use link predictions. Okay, so generally, if you are trying to analyze a network, you want to complete that network, and only then you want to test your algorithms on that network. Okay, so link prediction is also used for network reconstruction. Then comes another application, that is citation network. So in citation network, we have different researchers, right? Different researchers who are collaborating with different researchers. Now you want to identify a particular researcher in a certain research area, and you want to see whether like in future you can collaborate with this person or not. Okay, so in order to identify those kind of things, you have to do this link prediction algorithm. Okay, so with this slide, we have motivated ourselves enough for studying the link prediction algorithms further. Okay, so we have seen in short that there are a lot of application in online, a lot of application in social networks, e-commerce, military, then network reconstruction, citations, and so on. Okay, so in the starting of the lecture, I have told you that link prediction problem is of two types. Okay, so link prediction is a problem is of two types. So there are two ways of looking at this problem. It is one, first it can be for applied to the static networks, and the other is that it can be applied to the dynamic networks. Now, for the static networks, we try to predict missing links. Okay, so for the static network, we try to predict the missing links. So what is the goal here? The goal is to identify the edges that already exist but are not observed. Okay, so this is the goal of identifying missing links or predicting the missing links in the network. Now, this is for static graph, and it is common when you have incomplete data collection and you want to complete it. Okay, so you might have incomplete data collection, or you might have noisy data or hidden networks. So in order to complete these networks, we need something called as missing link prediction. Now, this is the second case. Okay, the second case when we apply link prediction to the dynamic networks. So in the dynamic networks, the network keep on changing. Okay, so we have snapshot of the network at T, we have at maybe T1, that is timestamp 1, and we have the snapshot of the data and timestamp T2. Okay, so from timestamp T1 to timestamp T2, there will be certain changes. Okay, so there might be certain edges that were not in T1 but are now in T2. So in using the link prediction, we try to identify those edges. So that were not there in T1, but are now there in T2. So yeah, so the goal of this problem is to predict edges that will form in future. Okay, and it is applied to dynamic or evolving graph. So this is commonly used in your social networks, recommendation systems, and citation networks. Okay, so now let me highlight the key differences between these two type of problems. The first component or first aspect is time. In missing link prediction, there is no time component. But like in future link prediction, you know that this is dynamic graphs and we consider time in this. Then graph type here is static, here is dynamic. What is the objective? Objective is to recover the hidden links, to recover the links that are not there in the network or that are missed or that are hidden. On the other hand, in a dynamic network, we are trying to forecast whether these people will be friends in future or not. Okay. And then data assumptions. Here, the assumption is that the graph is incomplete. And here, the assumption is that the graph is evolving over the time. So next, what is the difficulty? There is structural ambiguity, and here there is temporal uncertainty. Okay, so now, like till now, we have understood that link prediction problem is of two types, and we have understood the applications of link prediction. So now let's move to the mathematical part of this problem. Okay, so now at time t naught. Okay, so try to understand at time t naught, we have this graph GVE. At time t1, we have the graph V dash E dash. Okay, and this is time t1. And time t1 is greater than t naught. So this is simply the representation of the dynamic graph. Okay, so this is the representation of the graph that is changing from time t1 to t2, t naught. Okay, so whenever I have this graph, okay, so there are 5 different cases where the changes can happen. So let's try to understand these 5 variation of the networks. Okay, so you have this network at T naught, at T1, at the next time, there can be addition of new nodes. Okay, so you at time T naught, you do not have a certain node in the network, but at T1, you have an addition of new node in the network. Okay, so this is case one. Case one is new nodes are added, but they do not form any link. Okay, so new node is entered the network, but it do not form any links with the network. So then comes the second case. So what is the second case? We have new node as well as we have new links in the network. Okay, so we have new node joins. In the case two, we have new node joins and form new connections. Okay, so in case two, you have both addition of a node and the edges associated to it. In the third case, we do not have any new node added, but we have an edge added. Okay, so what is the third case? No new nodes are joined, but some new edges are formed. Okay, so now we come to the fourth case. In the fourth case, we have one edge that is deleted. Okay, and then in the fifth case, we have edge and a node deleted. Okay, so these are the changes in the network that can happen. Okay, so there can be addition of nodes, there can be an addition of nodes along with edges, then there can be addition of only edges, but no new node enter the network. There can be a case where certain edges got deleted. Okay, and there can be a case where certain nodes as well as the edges got deleted. So these are the 5 different cases. Now, there is one of this very important point to be noted here. So there are a lot of algorithm for link prediction. Okay, so generally, like we will be looking into these two cases. So in this case, we have edges added, and in this case, we have edges added along with the node. So generally, not also not this one, we will be mostly focusing on this case. Okay, and there is a lot of research that is done on this case, like addition of new edges. Why we are not considering addition of nodes? Because it is highly uncertain. Okay, so how can you predict a certain node will enter at time t1 or not? So this is like highly uncertain problem. So there are not many algorithms on these type of problems, but there are a lot of algorithms, a lot of research work is already been done in case number 3. But there is very less work that is being done in this case, the deletion of the edges and deletion of nodes and edges. So if you are looking for research problems, then you can maybe start working on these types of problem. So this is a very new problem where it is not analyzed that how you will predict the deletion of the edges in the network. Okay, so this is a new research area. And in today's lecture, we are mostly going to focus on this third case. Okay, so now this is again the definition of the link prediction. So I hope till now everyone must have understood this problem. I'll quickly go through this slide. So generally, like because we are considering case number 3. Okay, so because we are considering case number 3, we will be having a graph GVE. Okay, maybe at time t naught. Then at t1, we will be having g dash, maybe v e dash. Okay, so if you see that the vertices will remain same from t naught to t1, only the edges will change. And what will be the change? There will be addition of a few edges. Okay, so there will be addition of few edges, and these edges can be represented by this formula. Okay, so what is our problem? Our problem is basically to predict these edges. Okay, so now we have clearly understood the problem. We have clearly understood the motivation behind this problem. So now I want to understand that how difficult is this problem? Okay, so suppose we have about 100 nodes. Okay, so let us assume we have about 100 nodes. Then for very large graphs, there are approximately order of V edges. Okay, so number of edges will be approximately equal to order of V. So this is an assumption for large networks. But the maximum possible edges with 100 nodes is 100 C2. Okay, which comes to about 4950. So what are the number of edges, number of maximum possible edges with the 100 nodes? It's 100 C2. Okay, and its value comes to this. Now you see that there were about 100 edges. Okay, so originally, sorry, there were around 100 nodes. Okay, so the graph can have approximately 100 edges. Okay, some of these edges will be given. Okay, so when you have to solve this problem, some of the edges will be given. Some of the edges will be given. Okay, so then you have to identify very few edges. But actually, like total number of possible edges are these. Okay, so from these many edges, you have to identify, you have to predict very few edges that are correct. Okay, so you can see that this problem is very difficult. So because from these many samples, you have to choose only very few samples that are correct. So that is why we can argue that this problem is difficult. Okay. So now, what are positive samples? Positive samples. Okay, so this is just the explanation of what I have like already explained you. What are positive samples? These are the existing edges, the edges that will be there in the network. So they are approximately 100. Then what are the negative sample? Negative samples are the edges that do not exist. So it will be 4,850. Okay, so amongst these edges, you have to predict very few edges. So that is why there is a huge number of negative samples. So because there is a huge number of negative samples, this problem is also called as imbalance class problem. So I will be discussing this in more detail. So how this is a imbalance class problem. So yeah, okay. So yeah, so now we have understood that this problem is, difficult. So now let me explain you that given an algorithm, or like for example, you worked out and you came up with an algorithm for predicting the links. Now how will you check whether the algorithm is performing correct or not? It's very important to check whether the algorithm or the predictions are correct or not. So now next topic that we are going to study is evolving link prediction method, train and test plates. Okay, so now let us try to understand how we are going to check whether the algorithm is correct or not. Just give me a second. Okay. So now, like first of all, in order to check your algorithm, you have to divide your data into train and test. So first of all, let us consider case one. So what was case one? Case one was when you were trying to predict the missing edges. Okay. So in this problem, suppose you have graph G, V, E. All right. So in this graph, you want to divide your edges. So basically what problem we are solving? So we have this graph G, V, E. Okay. Then later on, we have the graph GVE dash. Okay, so there will be certain edges that will be inserted in the static graph. So what will be those edges? It will be E dash minus E. So the problem is to identify these edges. So the problem is to identify these missing edges. Now, in order to solve this problem, suppose I have an algorithm and that algorithm has predicted certain edges and I want to test that algorithm. So for that, first of all, what I will do is I will divide my edges into E-train, that is my train data, and test data. Okay, so the edges will be divided into train data and test data. So suppose initially I had 100 edges. Okay, so how I will divide? I will follow 80-20 rule. So 80 edges will be in my train data and 20 edges will be in my test data. Now, how I will test? I will remove these 20 edges. Okay. So what you will do, you will remove these 20 edges. And after removing, you will apply your algorithm. You will apply your algorithm and you'll try to identify that whether your algorithm can predict these 20 edges or not. Okay. So then you'll apply the algorithm and try to identify that whether these test edges can be predicted or not. Now, next question comes is how you will remove these edges. How you remove the edges. Okay, so can anyone guess that how can we remove the edges? Is it random or it can be based on certain metrics? How are we going to remove the edges for test data? Anyone would like to answer this question? Okay, so one way is randomly deleting the edges. Okay, so you will randomly delete the edges. Other is based on degree or some notion. Okay, so maybe based on degree or some notion, you can delete the edges and then you can check that whether your algorithm is performing correct or not. So we will mostly use this method. Okay, so how we will use this method? So why using this method is important? So let me explain you with the help of an example. So suppose I have this particular network. Okay, so this is a particular network that I have. Okay, so now let us suppose this is A, B, and C. Okay, so these are the nodes A, B, and C. And let us assume that I consider this particular edge. So I'm considering this particular edge as test edge. Now, since you can see that B and C have common neighbor as A. So because B and C nodes have common neighbors, so it is easy to predict this kind of edge. Okay. But on the other hand, let me assume a second case. So in the second case, let us assume that we have this edge. Okay, so if we have this edge in our test data, so what will happen is, so because this particular node, let us assume that this is D node. Okay, so now we have this D node. So now if you remove this edge, so whether your algorithm can predict this particular edge or not. So the answer is it's really difficult for your algorithm to predict these kind of edges. So it is difficult to predict. Why? Because these two nodes are very far. These two nodes, node D and node B, are very far and there are no common connections. So it's very difficult to predict the bridge edges. It's very difficult to predict bridge edges because like removing these bridges can also lead to disconnecting the graphs. Okay, so this was our first case. Okay, so now based on this algorithm, like how will you, form your test data? Whether it will be random or based on the degree. So which one do you think is correct?
And based on degree will be better.
Based on degree is better, but don't you think it will be biased then? So if I want to prove that my algorithm is better, then I will choose all the edges that can be easily predicted, right? So yeah, so this is your homework. Okay, so you need to identify that what should be the basis of identifying the test data. Okay, so you should think on this question. Should I remove it randomly, or should I, use degree for that? Okay, or some other notion for that. So what should be the strategy used for removing the edges? I will ask this question in the next class. Okay, so this is very important question. So please try to think and work on this question. Okay, so this is the first case that we have covered. So we have covered when when we were trying to predict the missing edges. So now we know that in a link prediction, there is another case. Okay, so what is case two? So case two is when the task is to predict future edges in dynamic graph. Okay, so this case is pretty straightforward. So at time t naught, you will be having graph GVE. At time t1, you will be having graph GVE dash. Okay, so there will be certain new edges, E dash, that will be added. Okay, so that will be added to the original subset of the edges. So what you want to predict? You want to predict E dash minus E. Okay, and this becomes your test data. Okay, this becomes your test data. So you already have the edges and you already have the ground truth that in future these will be the edges that are added, and those new edges you can use as your test data. And the remaining edges, those were the E edges. E edges were the edges that were originally there in your graph at T naught. So this can be considered as your trained data. Okay, so yeah, so I hope you have understood till now. Any questions, anyone? Any questions anyone want to ask? Okay, so now let me review on what we have covered before. So let me mathematically write that how this problem was difficult. Okay, so when you have, suppose you have V nodes. Okay, suppose you have V nodes. So in this particular case, how many pair of edges are there? How many possible pair of edges are there? So suppose I have V nodes. So we have already done an example where I considered that there were 100 edges. So now if there are 100 nodes, sorry. So if I have 100 nodes, then how many possible pair of edges are there? If I have V nodes, how many possible edges are there? Anyone?
You
We
mentioned V
see
equals
two.
to E. Yeah.
Correct, correct, correct. So the answer is we see two pair of edges. Okay, so suppose E edges are already given. Okay, so these are the number of edges that are already given to you. Then how many edges you have to predict? How many edges you have to predict? If these were the total pair of edges, these edges are already given. So how many edges you have to how many edges you have to predict?
Subtraction of this. We see 2 minus C.
Okay, so the answer is, so there will be VC2 minus E non-connected edges. Non-connected edges. Okay, so these are the non-connected edges. Now E was already given. Okay, and we know that for large graphs, number of edges that will be there will be approximately equal to order of v. Okay, so because it will be approximately order of v, so in this sample, so you have to consider this sample. From this sample, you have to predict very, very few edges, and those will be about 0.5%. Okay, so about zero point 0.5 edges you have to predict that will be connected, because like we are assuming that total number of edges are order of v. Okay, so now we know that what is positive sample? What is positive sample?
He had just given, right, ma'am? That's a positive.
Yes, yes. So these are the edges which are already connected. Then what is negative sample?
Non-connected, that
Yes.
which we
These are
derived.
the edges which are non-connected. So you can see that in this particular problem that we are trying to solve, in this particular problem, the negative sample is very, very huge as compared to the edges that you have to predict. Okay. So because the negative sample is huge, so this is a inherently imbalanced classification problem. Okay. So I can say that this is imbalance classification problem. Okay, so now let's discuss how this is classification problem. So you might have studied classification problems in your prior courses. So how do you think this is a classification problem? Can you mathematically define this problem as a classification problem? Anyone want to try?
When we say classification, ma'am, actually, any sample given to
Mm-hmm.
identify it is a negative or positive, right? It's a, I mean, yes or no kind of a.
Yes. So we are given the samples. Okay, so what we will be having? So we will be having all the pair of edges, all the pair of nodes. Okay, all pair of nodes. So between these pair of nodes, okay, I want to check that whether there is an edge or not. Okay, so this is a binary classification problem because for each pair of node, x and y, let us assume, for each pair of node, I will predict it either as 0 or 1. 0 means there is no edge, and 1 means there is an edge. Okay, so we are going to predict these labels for each and every pair of nodes. So this is how this problem is a binary classification problem. And it is important to note that it is imbalance classification problem. Therefore, we have to use special metrics for the evaluation of the algorithm. So anyone knows this, that like whenever we have an imbalance classification, what are the metrics that you will use to evaluate your algorithm?
We can use confusion matrix.
Yes, in the using the confusion matrix, what can you use? Can you use like the accuracy, recall, what you will use for that?
It's F1 score we have to use, man, because accuracy may be totally. Sometimes it will be very, very accurate, but precision and recall will be very bad.
Correct, correct,
So we
correct.
have to go for F1 scores. So that will.
Okay, okay. Sure. So now we will take a small break. And after the break, we are going to discuss the evaluation metrics. So I think you have little bit idea about the confusion metrics and the problems related to that. So I will be quickly going through those problems and I will be telling you how to evaluate these methods. Okay, so we will meet after 10 minutes now. Okay. Hello, everyone. Welcome back. Okay. So now you all might be having an idea about confusion metrics. So let me give a quick recap of the confusion metrics. Okay. So now in terms of link prediction, like we will try to understand confusion metrics. So confusion metrics is a matrix where we have actual labels and the predicted labels. Okay, so let us assume that here we have actual labels and here we have the predicted labels. Okay, now we have already defined link prediction as a binary classification problem. And in the binary classification problem, I have told you that there will be two labels. One will be one represent that there, like the algorithm predicts that there will be an edge, and zero represents that there will not be an edge. Okay, so there will be two labels. Actually, that is the ground truth of the data. So this will be 1 and 0, and these are the predicted labels 1 and 0. Okay, your algorithm will be predicting that whether a particular set of nodes, a particular pair of nodes, X and Y, they have an edge or not. Okay, so yeah, so we have these labels. Now these labels can be divided into different terms that are called as true positive, false negative, and true negative. So let me explain you quickly what all are these terms. Firstly, when you have, let us suppose you have some 100 value here. What does this mean? This means that for 100 such instances, your algorithm has predicted that there is an edge, and there was actually an edge in the network there. Okay, so this is true positive. Okay, true positive is like when your algorithm predicts it true, and that is actually true. The count of how many times the model predict the link to be formed, okay, and it is actually formed. So this is true positive. Next, like actually there is no edge, actually it is 0, but our model is predicting it as 1. Okay, so our model is predicting it as positive, but actually it is not true, so this is false positive. Okay, so now we have this case that actually there is an edge. Okay, but our model is predicting it as not having an edge. So the model is predicting it as negative. This is false negative. Okay, and then we have true negative. So there was no edge and it was predicted as no edge by the algorithm. So this is true negative. Okay, so these are the definitions for true positive, false negative, and false positive. Now, I have one question for you. Just a second. Okay, so now given this confusion matrix, I want you to calculate these values. So you have to calculate the actual non-edges from the confusion matrix, and you have to tell me what will be the formula for predicted edges. Total number of predicted edges, total number of actual non-edges. So I'll give you 2 minutes for this question. What are actual non-edges? I hope you all understood the question. So you can either write in the chat box or, use your microphone to answer this question. What are total number of non-edges? What are actual number of non-edges? Anyone wants to answer?
Now it's true negative plus false positive.
Correct. So it's true negative plus false positive. So how? So true negative is जहाँ पे edges नहीं है. तो यहाँ पे we will
नहीं.
get one value जहाँ पे edges नहीं है.
Yes. No.
Right? And then we have false positive. Okay? False positive means उसने predict तो किया था कि edges हैं. But actually में edges नहीं थी. Actual data में edges नहीं थी. So it will be summation of these two values. Then what are the total number of predicted edges? So
It's
this
true
is
positive plus false positive.
correct. So yeah, so like you can get these types of question, like you need to understand this confusion matrix very clearly. So you can get these type of questions as like 1 marks question or 2 marks questions. Okay. So yeah. Okay, so now these are the different evaluating methods. So firstly, we can have the metrics called as accuracy. So what is accuracy? Accuracy is the ratio of total number of correct predictions. Okay, so total number of correct prediction divided by total number of predictions. Okay, so we will study like in the following slide that why accuracy is not a good formula for calculating the performance of an algorithm. So this is the formula for that. Okay, next we have precision. So what is precision? Precision is that out of all the positive predictions, okay, out of all the positive predictions, how many are correct? Okay, so in this case, you are considering all the positive predictions. Out of all the positive prediction, that is total positive and false positive. Okay, so these are all the positive predictions. So out of all the positive predictions, how many are correct? ओके सो तुम्हारे एल्गोरिदम ने जितने भी लाइक पॉजिटिव प्रिडिक्ट किए उसमें से हाउ मेनी आर करेक्ट सो दिस इज प्रिसीजन so next we have recall. So what is recall? Out of all the actual positives, out of all the actual positive, see there is a minute difference here. This is predicted. This is all the positive predictions. Precision is out of all the positive predictions. This is actual positives. Okay, so actual positive will be total positive plus false negative. Okay, so total positive plus false negative. So it is out of actual positives, how many are correct predictions? So yeah, so this is your accuracy, precision, and recall. Then we have another evaluation metrics that are true negative rate, also called as specificity. This is out of all the links that are actually negative. Okay, so out of all the links that are actually negative, how many are predicted negative? Okay, so out of all the negative, how many are actually negative? Out of all the negative predictions, how many are actually negative? Okay, so that is true negative rate. Then we have false positive rate. What is false positive rate or fallout rate? This is out of all the negative samples. Out of all the negative samples, how many are wrongly predicted to belong to a positive class? Okay. So now for link predictions, like we do not use the accuracy, but we have to use other metrics. Okay, so now before going further, I would like you to quickly go through this question. Okay, take some time and you need to find true positive, true negative, false positive, and false negative. Okay, so this is the network that you have. The yellow edges are the actual edges. Okay, so the yellow edges are actual edges and green ones are the predicted edges. Now you have to calculate true positive, true negative, false positive, false negative. So what is the value of true positive here?
Two, ma'am.
Correct. So out of like actual edges, how many were truly like predicted as positive? So this is two edges, that is AB and BC. Then what is the value of true negative?
Again, two only, ma'am.
Correct. So there are two edges, that is AD and AC. Okay. So these two edges were not there in the original data and they were not predicted. Now what is false positive?
One, ma'am.
Correct. And what is false negative?
One only.
Correct. So yeah, so you should understand all these terms and you should be aware of all the matrices that we have covered. Okay, and you can be asked numericals from these questions. Okay, so yeah, so this is the question that you can practice and like you can calculate accuracy, precision, recall, and all these values from this graph. Okay, so now let's discuss that how like the accuracy is not a good measure. Okay, so now typically let us assume a network and the network have nine negative edges. So let us assume that the network have nine negative edges and one actual edge. Okay, so there is one actual edge and nine negative edges. Now, a typical prediction model. Let us suppose that I have a prediction model and I have predicted that all the edges are negative edges. Okay, so let us suppose that मैंने randomly बोल दिया कि all the edges are negative edges. Now in this case, you can see that these are the values. Okay, so what will be the accuracy? Okay, what will be the accuracy? The accuracy is using this formula. True positive plus true negative, then we have this summation. So if you use this formula, you can see that accuracy will come to 90%. Okay, so it will come to 90%. So which is a huge value. So in this case, it will be 9 upon 10. Okay, so your accuracy will be 9 upon 10 if you calculate. So the accuracy is 90%. So you can see that accuracy is not a good measure when you have this huge imbalance in your data. Okay, so you have to take this into your mind that I have explained you that this is an imbalance classification problem. So whenever you have imbalance classification problem, you cannot use accuracy. So even like before going to break, I have asked this question that which algorithm you can use. You can use F1 algorithm, but that is not like the best choice. Okay, so for link prediction, we have a method called as AUC ROC. So this method is used to, to evaluate your algorithm. So in this algorithm, we will plot the false positive rate and the true positive rate. Okay. So for the different algorithms, we can plot these, and the curve that has maximum covered area under it, that is considered as the best algorithm. Okay, so now we will move on to, after like understanding about the evaluation of a link prediction method. So next we are going to see what all are the actual algorithms for predicting links. Okay, so this problem can be divided into three types of algorithms. So we have heuristic based methods, then we have probabilistic methods, then we have theoretical models. Okay, so now we will be covering these algorithms. We will also be covering few algorithms from here. Okay, and we are not going to cover the algorithms from this part. So heuristic model is based on the local similarity method and the global similarity method. So we will now in the following slide study about the local similarity matrices. Okay, so now, first of all, let us try to understand what is heuristic method. Okay, so now irrespective of the techniques used, the underlying idea of link prediction is to successfully connect nodes that share similarity. Okay, so what is important here? It is important to note here that we have to connect those nodes that have some type of similarity. Okay, so there should be some type of similarity between the nodes, and using some heuristic method, we will identify that similarity and we will try to connect those nodes. Okay, and we will try to predict an edge there. Closer similar two nodes are, the more likely they are to be agreement, or more likely they are interact. Okay, so more similar two nodes are. We have also studied like the concept of homophily. So when we were studying this community detection algorithm, so we have studied the concept of homophily. Okay, and in homophily, I have given you a lot of examples that like how similar people tend to connect. Okay, we generally whenever like we become friends with other people, we try to find कि ये बंदा मेरे से similar है या नहीं है. Okay, and yeah, so that is the concept that more closer or more similar two nodes are, more likely they are to be connected. Okay, so this is the idea of heuristic model, and using certain heuristics we are going to identify this similarity. Now similarity can be based on node properties. You have seen that there can be various node properties. The node properties we have studied in the chapter of centrality. Okay, so we have studied that there was different types of centrality like degree, betweenness, eigen. So we might want to identify the nodes that are similar in terms of these node properties. Okay, then there we also want to find the similar nodes based on the edges or the connections or the relationships. Okay, so then like the third is metadata related to nodes. Okay, so metadata is the properties of the nodes. So whatever, like I go to gym, then there is another person who goes to gym. So this is the metadata related to the node. Okay, going to gym is a metadata. Okay, so this type of metadata can also be used to calculate the similarity between the nodes. More attributes that are similar, more metadata that is similar, more likely it is that these two nodes will form a connection. Then heuristic measure of a structural similarity. So in the structural similarity, we are going to see local heuristics, okay, and we are going to see global heuristics. We are also going to see the heuristics that are between local and global that are called as quasi-local heuristics. In today's lecture, we will be able to cover only local heuristics. The global heuristics and the quasi-local heuristics we will be covering in the next lecture. Okay, so the first measure is based on homophily. Okay, so you know that the nodes, they have some neighbors. So we will try to identify common neighbors. Okay, so we have this node A, we have this node B. Okay, and we will try to identify the common neighbors between these two nodes. More the number of common neighbors, more is the probability that these two people will eventually become friends. Okay, so if there are two people, okay, and they have many common friends, okay, so they have many common friends, more the number of common friends they have, more is the likelihood that these two people will eventually become friends with each other. So this is also called the concept of triadic closure. Okay, so this is also called as triadic closure. Okay, so now how we will quantify this value? We will quantify this value by identifying the common neighbors. Okay, so for example, we want to identify the similarity between node A and C. Okay, so this is node A and this is node C. Now you want to identify the similarity between these two nodes. So firstly, what you will do, you will try to identify what all are the neighbors of C. So the C has neighbors D, then F, okay, then it has E. Then we try to identify what are the neighbors of node A. Neighbors of node A are F, then we have D, then we have E, then we also have B. Okay, so you can see that there are three common neighbors between these two. So more the number of the common neighbors, more is the likelihood of two nodes of more is the probability of having an edge. Okay, so how these algorithms will work? So what you will do, you for each pair of node, you will try to identify this value, the similarity value. Then you can sort based on the similarity value. And from the sorted value, you can choose maybe top 1% or 2% to be to be as predicted edges. Okay, so from these sorted similarity values based on descending order, so from the highest similarity to lowest similarity, you will order the nodes. And once you ordered these pair of nodes, okay, top maybe like 1% or 2%, you can choose it as the edges. Okay, so now there comes the next algorithm, that is Jaccard similarity. So now you can see that this particular algorithm was not normalized. Okay, so it can happen that there is a node C that has just one connection, and then there is this node A that has a lot of connections. Okay, so now this particular algorithm is not considering this fact that like C has very few edges and A has more edges. Okay, so in order to avoid this situation, you have to use normalization. So how do we normalize? We normalize using Jaccard similarity. So in the Jaccard similarity, you have common neighbors in the numerator, and in the denominator, you have union of these two neighbors. Okay, union of these two sets. So you can see that we have already calculated the intersection of the neighbors was 3, and the union of these neighbors is 4. Okay, so based on this, you can calculate the Jaccard similarity. Again, like for each pair of nodes, you are going to calculate this checkered similarity, and then you are going to sort those values in descending order, and then you are going to choose top few edges as the links. Then there are certain other algorithms as well. For example, Salton index, also called as cosine similarity. So you might have heard about these terms. So in this case, in the numerator, we are taking the intersection between the common neighbors, okay? Common neighbors between the nodes. And in the denominator, we are taking the degrees of those nodes, okay? And we are going to penalize it by a root function. Okay, so then in addition to this, we have the third algorithm, that is preferential attachment. Now, what is preferential attachment? So I have explained this term before. Anyone remembers what is preferential attachment? What is preferential attachment? Okay, so preferential attachment is that in a network, you tend to connect to popular people. Okay, so what do I mean by this? You tend to have, like, suppose in your network, you have maybe some celebrity. Okay, so now you will try to develop the connection with those popular people. By popular, I mean that the nodes that have high degree. Okay, so in this case, we are going to quantify the preferential attachment. Okay, preferential attachment is when a node tries to connect to another node that has very high degree. Okay, so how do we quantify the preferential attachment? So this is so this measure is the derived concept from preferential attachment of scale-free networks. The likelihood of a node to obtain an edge is proportional to the degree. Okay, it is proportional to the degree. Now, preferential attachment can be quantified by degree of node X into degree of node Y. Okay, so for example, you want to identify the similarity between A and C based on preferential attachment. So what you're going to do, you are going to consider the degree of C and you're going to multiply it by degree of A. Okay, so yeah, so there are these different algorithms, and these different algorithms can be used based on your application. Okay, so based on your application, you have to decide that what is the link prediction algorithm that you are going to use. So in the first slide, I have told you that there are a lot of applications. Okay, so based on those applications, so like where you want to use and where which algorithm will fit. So you need to identify those concepts. Okay. So yeah, so next algorithm that is again very popularly used, that is called as Adamic Adar. Okay, Adamic Adar, these are the two scientists on which the name is given. Okay, so now in this case, let us suppose we have A and maybe C. Okay, so now we have this node B that is a common neighbor, and B has a lot of other connections. Okay, at the same time, we have another neighbor that is D, and D do not have any other connection. Okay, so now suppose D gets any information. Okay, so if D gets any information, it is very likely that D will share it to A and C. Okay, but on the other hand, since B has a lot of connections, a lot of other connections, so like it can happen that B do not share the information with A and C. Okay, so now this particular algorithm, it try to penalize the nodes that have high degree. Okay, the neighbors that have high degree. So in order to penalize, so what is the formula for this algorithm to calculate the similarity? So firstly, we are going to calculate the common neighbors. Okay, so we are going to consider the common neighbors, for example, B and C. And for each common neighbor, okay, we are considering its degree. So kz is the degree of the neighbor. Okay, so kz is the degree. So we are going to penalize that node based on the degree. So this forms this forms the formula for this algorithm. So we have another formula, that is resource allocation index. So in resource allocation index, rather than using log value, it is straight away using the degree value. Okay, so here it is using log, here it is not using the log. In this formula, we are only considering all the neighbors. And for those neighbors, we are using the degree of each node. For example, in the case of A and C, we had three common neighbors. What were those three common neighbors? One was F, then we had E, and we had D. Okay. So now what was the degree of each of these node? The degree of D is 3. Here we have degree 3. Here we have degree 3, 4, 5. And this is how we calculate Adamic Aadhaar similarity. Okay, so I hope these formulas are clear to you. So we have already covered Salton index, that was cosine similarity, commonly used commonly used metrics to measure the similarity between pair of documents embedding in the vector space. Okay, and this is how we calculate this formula. So I have explained you in the previous slide. There are a few other ways of normalizing normalizing the common number of common neighbors. So this can be, one of the method is hub promoted index. So in hub promoted index, you use the minimum degree. So minimum degree from the two pair of nodes that we are considering. And then we have hub depression index. In hub depression index, you use the maximum degree of these two. Okay, so this is all about the local methods. Now, since we have time, let's like briefly discuss the global method. Okay, so now we have covered all the local methods, and in the local methods, you have seen that like we use local node properties in order to identify the similarity between two nodes, and based on those similarity, we are going to predict the links. Now, global heuristic, as the name suggests, global heuristics consider the entire network rather than the local neighborhoods that was there in local heuristic method. Okay, so here we are going to consider the global heuristics, the entire network. So this particular algorithm is inspired from card centrality. Card centrality is a variation of PageRank algorithm. So we have covered PageRank algorithm in our previous lectures, and this is a slight variation of the PageRank algorithm. It takes into account the influence of the neighbor beyond hop one. Okay. However, longer the path length, less likely the ends influence each other. Okay, so in this particular case, what we are going to identify, suppose like we are calculating that we are predicting that whether there will be edge between X and Y. Now, we are going to see like starting from 1 to infinity. Okay, so we are going to identify that how many paths of length 1 are passing between x and y. Okay, how many shortest path of length 1 pass through x and y. Then we are going to see 2. Okay, so how many shortest path of length 2 passes through x and y. Okay, and then we are going to see that how many shortest paths of length 3 are passing through x and y, and so on. Okay, and more the path length, more we are going to penalize it, and alpha is the value that can penalize that matrix. Okay, so alpha can be, for example, 0.5, and like as the path length increases, for example, 3 or 4, okay, so this will have less impact on the similarity. Okay, so this is the idea about heuristic cards method. So we will be covering a few of other global methods in our next lecture. So yeah, so now I will give a quick recap of what we have done today. So in today's lecture, we started with a link prediction algorithm, a link prediction problem. We have tried to understand what this problem is. So after understanding this problem, we concluded that link prediction problem can be viewed like either as a static network or on the dynamic networks. Okay, so these were the two variations of this problem. Then we have seen a lot of application of link prediction, and we have seen how this problem is a difficult problem. And then we have tried to identify that what will be the evaluation methods if we come up with some algorithm for predicting the links. Okay, and then like we also started with various methods to identify to predict the links in the network. So mostly these were based on heuristics. So we have covered all the methods that are based on local heuristics. And then we started with the global heuristic methods. So in the next lecture, we will be discussing in detail about the global methods. And then we will be covering few probabilistic algorithms as well. So yeah, that's all from my side, class. Do you have any question from today's lecture?
No, thank you.
Okay. So sure, with that, we will end today's lecture. So thank you, everyone. Thank you for being a lovely audience. Bye.
Thank you, ma'am.
Okay,
Thank you very
thank
much.
you, ma'am. Bye.